All right, everybody. Welcome to the second week of class. Today we're going to start talking about probabilities. We're going to go over a lot, basic concepts, and end up with sensitivity, specificity, and positive predictive value. These are all important concepts to learn, especially if you're in the health sciences. Let's just go through some definitions. Start with an event. An event is some outcome of interest. It could be the outcome of it is the outcome of a random experiment. For instance, flipping a coin is an experiment. The outcome of the flip can be heads or tails. That's the event. Rolling a fair die. Some people like to say dice these days for one, but it's actually die. The outcome is 1, 2, 3, 4, 5, or six-sided die. I know there's some different die for different games. Individual body mass index is another example of an event. Events are elements of a sample space. So here's some examples of different sample spaces. In this event, we have sex, and in this case, we have male and female. We have a roll of a die. We have those 6 possible outcomes, 6 possible events, right? Those events make up the sample space, right? And then we have body mass index. You could have like an infinite number of body mass indices or values for a body mass index, I should say. Okay. So the sample space is composed of all possible events for sex. Now we're talking about biological sex again, you could say gender and whatever, but let's just stick with at this moment that there being 2. So you have male and female, right? So those are the only 2 possible outcomes of that sample space. And then for a roll of a die, there are 6 possible outcomes with a 6-sided die. And then BMI, like I said, there's many values for BMI. So those are, but it's composed of all possible outcomes. There are no other outcomes in there. Probability. Now, some people could say that the empty set is a member of every sample space, and it is, but it's not. Let's just not worry about that right now. Okay. Probability is the proportion of times an event is expected to occur in the population. So we're always dealing, like I said before, with samples being estimates of population parameters. So what's the probability of landing heads? Heads, if you flip a coin, you have 2 possible outcomes, heads or tails. Probability of heads, right? So again, the proportion of the time the event is expected to occur, it's 1/2 or 0.5. By the way, that doesn't guarantee you that if you flip a coin, you're going to get, like you flip the coin twice, once you'll get heads, and the other time you'll get tails. There's no guarantee of that. It's possible you could, flip a coin 10 times to get 10 heads in a row, right? There's no, well, since we've got 10 in a row, the next one has to be tails. Each individual trial is independent of the other trials. So their probabilities are memory-less, so that they don't remember what happened last time. Just start all over again each time you roll. You flip the coin, but over the long term, you'd expect to get 50% heads and 50% tails. The probability of rolling a fair die is, well, there's 6 of these possible outcomes here, right? And probability of rolling a 6, it's 6 divided by, I'm sorry, there's only 1 6 in here, so it's 1 divided by 6. So there's 6 possible outcomes. It's 0.167. So let's look at some properties of probabilities. Some people call these axioms. Probabilities range from 0 to 1, so they cannot be negative and they cannot be above 1. So if you ever see a value that's negative for a probability or above 1, you know there's something wrong there. Property 2 is probabilities in a sample space S. I guess we're talking about the sample space of all possible events, but we say all possible individual mutually exclusive events must add up to 1. Mutually exclusive means they cannot co-occur, like heads and tails cannot co-occur. So the probability sample space always has to be 1. So if we took every possible body mass index from smallest to largest, every possible one, that would encompass 100% of all possible events, right? If we divide 100 by 100, we get 1, right? You can go back and forth from proportions to probabilities, right? By dividing by 100, percentages to probabilities dividing by 100. Imagine that 4 individuals are running a race and we have data on past performance. Using these data, we compute the probability of each racer winning the race. So this is my sample space. There are 4 individuals. Each one has a probability. So the probability of each of these events is listed here under probability of success. Success in this case is winning the race, 0.15, 0.34, 0.41, and 0.10. Well, according to this axiom, the probability of the sample space has to be 1. So if we summate, we add up all these different events within the sample space, we would get 1. So we do that. 0.15 plus 0.34 is 0.49 plus 0.41 is 0.9. 0.10 is 1. So there's your sample space. It adds up to 1. Property, excuse me. 3, the complement of an event is the event not happening, right? People will argue that there's more than one complement to an event. Again, you can have things like the empty set as well within a sample space. Let A be, but let's just say that there's either or in these sample spaces. Let A be the event, be an event in the sample space S. So again, we'll use S for sample space. Let not A be the complement of event A. Notice that I have a bar over the A that represents not A in this case. And you think, why would you say not A? Well, it's easier than saying 1 minus A all the time. So if the probability of the event, if probability of A is the probability of event A, probability of the complement of A is 1 minus the probability of A, right? Similarly, well, yeah, that's it. Yeah, the complement of the A's probability of not A is 1 minus probability of A. You could also say probability of A is 1 minus the probability of not A. So they're just complementary. The reason we can do this is because the sample space has to add up to 1. And like I could say, what's the probability of racer 1 winning the race? 0.15. Probability of racer 1 not winning the race is 1 minus 0.15 or 0.85. Or you could add these all together, right? 0.34 plus 0.41 plus 0.10 to get that 0.85. Property 4, probabilities of disjoint events can be summed to provide the probability of either event occurring. Disjoint events is the same as mutually exclusive or complementary events. Those are events that cannot occur together. So there's no overlap between them, right? So the probability of A or B occurring is equal to the probability of the union. So or is the same as union. So this U here means union. Probability of A or B is equal to probability of A union B, which is the probability of A plus the probability of B. Think of or being synonymous with union and addition. Right? So we can add things together, and we just did that in the last example. Here's an example of cumulative probability where we can add things together. Like we have this vaping variable where we have vaping status, vaped at least once, vaped in the past 6 months, vaped in the last 30 days, vaped today. So there's 4 different levels of vaping. And each one has its probability. Like for instance, it's 15% chance that, again, if I want to convert this to a percent, I multiply by 100, 15% chance that somebody vaped today, right? So it says using the data in table 2, what's the probability that X is less than or equal to 3? All right, well, we call this value X, right? This is a variable X. It has different values 1, 2, 3, 4, representing these different levels of our variable. And the question was, what's the probability that X is less than or equal to 3? Well, these are mutually exclusive events, so we can add them together. So it's 0.4 plus 0.25 plus 0.20, right? Because less than or equal to 3, it's 0.85. And by the way, that's the same as the complement of vaping today, because these are all complementary to vaping today. So it's 1 minus 0.15 is 0.85. With continuous random variables, we have no discrete values. When we talk about discrete values, we talked about that last week, like there's discrete mass associated. Like for instance, there's mass here, right? There's mass for each of these, and the mass is representing the amount of people that make up this 40%, right? If there was 100 people, that would be 40 people, right? So it'd be 25. That's the mass here. But when we're dealing with continuous variables, we don't have that mass for each one of our values because probability of any given value can be really, really small because we can break this down. It's infinitely divisible. We can divide it into such small units, right? So what we do, but because of that, the probability of a given outcome in a continuous variable is always 0. So in order to determine probabilities, we look at the probability between 2 points. Like here, what's the probability one weighs between 160 and 170 pounds? We're not going to look at 160 or 170. We're looking at that area right here between 160 and 170. So when we have a continuous variable, we use the area under the curve between 2 points to find the probability. Actually, the way I would do this, I'd say what's the probability that one weighs less than 170, so all the way here to the left, minus the probability that one weighs less than 160, so minus everything here to the left. So that would give us the space in between. Let's continue with probabilities and rules. Let's look at the addition rule of probability. We kind of dealt with this already when we said we could add two mutually exclusive events, right, to get the probability of either of the two occurring. Well, that's not always going to be the case where we have mutually exclusive events. Sometimes there can be overlap between two events. So the way we would deal with that is we would subtract one portion of the overlap. So let's look at this. The probability of A or B occurring is the probability of A plus the probability of B. This is what we saw before, minus the probability of the joint occurrence of A and B. So we have the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B occurring. The joint occurrence is the intersection of two events, and this is the symbol for the intersection. So let's take a look at this, why we would do that. So this Venn diagram is really nice in demonstrating why we subtract this portion right here. So this is where the overlap is. If I didn't subtract it, I would count it once for A and I would count it again for B. So we don't want to double count this little area. So we subtract one of those portions of overlap. When we have mutually exclusive events, there is no overlap. So those two circles will be separate, right? So then that overlap, probability of A and B occurring would equal 0. So that's why the earlier equation I showed you was probability of A plus probability of B equals the probability of A or B. Okay. Let's do an example. Probability of cat ownership is 0.35. That means 35 of 100 people own a cat. The probability of dog ownership is 0.30. It means 30 out of 100 people own a dog. The probability of cat and dog ownership is 0.15. So notice that I have intersection associated with and is 15%. So what's the probability that one owns a cat or a dog? So it add together the probability of cat plus probability of dog minus probability of cat and dog. And we get 0.5. Some more stuff about pets. Another example, we can judge whether or not two events are independent. Independent means that event A does not influence the probability of event B. It means knowing A does not give you information about the probability of event B. Knowing the probability of event A gives you no information about the probability of event B. So we can judge to see if two things were independent. Well, if the probability of A and B occurring is equal to the probability of A times the probability of B, then we can say that the two events are independent. All right, so let's take a look at this. Because I gave you data on dog and cat ownership, I said the probability of owning a cat and a dog is 0.15. So that means I could take the probability of owning a cat and multiply it times the probability of owning a dog. If that does not equal to 0.15, then the two are not independent. So we multiply 0.35 times 0.30 and we get 0.105, which is not equal to 0.15. So therefore, owning a dog and owning a cat are not independent. It makes sense too, because people love pets, they're more likely to own a cat if they own a dog, or vice versa. This is what we call a cross-tabulation table. We're going to look at this table. One thing we want to know is marginal probabilities, conditional probabilities. Things that we want to know are marginal probabilities, conditional probabilities, and joint probabilities. We'll use all that for many different things. So this is a fictitious table that shows some survey on winter sport participants. Did you participate in a snow sport last winter? Yes or no? Could be skiing or snowboarding. Did you mountain bike at a ski area last summer? Well, ski areas have to make money during the summer months, so they generally convert their area into something else, like either some kind of a fun entertainment park with zip lining and stuff like that, or cycling, mountain biking, I should say. Okay, so these values going across here represent whether or not one participated in a snow sport. So 70 did and 930 didn't out of 1,000. These are marginal values, right? They ignore the second variable, right? Did you mountain bike at a ski area? 140 did and 860 didn't. We ignore whether or not they skied when we look at just these values here. These are marginal values as well. These marginal values add up to 1,000. The values in the center here are the joint distribution of the two. Like these 45 people did both skiing, snowboarding, and mountain biking, whereas these 95 individuals only mountain bike, but they did not ski or snowboard. Okay. So let's calculate marginal probabilities. The probability of mountain biking last summer, well, there was 140 people mountain biking out of 1,000. So it's 0.14. Okay, that's all you have to do for marginal probability. Conditional probability, well, we have to keep in mind what the condition is. So the occurrence of event A influences the probability of event B, right? So they're not independent in a sense, unless this is 0. So let the probability of B given A represents the conditional probability of B given A. So remember, there's this line here that represents the condition. Right? It probably should have been a curved, slanted line. That's okay. So by definition, we can calculate the probability of event B occurring given that event A occurred using this equation, probability of A and B divided by the probability of A. All right. So long as, obviously, and I say obviously because you cannot divide by 0, probability of A is greater than 0. Let's go back to the last pet example. So what's the probability of owning a dog given one owns a cat? Well, we know that the probability of owning a dog and a cat is 15% or 0.15. And we know the probability of owning a cat is 0.35. So if we divide 0.15 by 0.35, we get 0.429. So let's verify our joint probability of owning a dog and a cat. But I gave you earlier, I gave it was 0.15, right? What we do here is we just rearrange the equation, right? If I want to know what the probability of owning a dog and a cat is, right, I'd multiply both sides by the probability of owning a cat. So that would eliminate or cancel out the probability of owning a cat here, and we'd put it over here, right? And that's what I did here. I moved this numerator to the left side of the, excuse me, the equal sign, and then I moved what was on the originally on the left side to the right side. So I get the probability of owning a dog and a cat is the probability of owning a dog given one owns a cat times the probability of owning a cat. We get this 0.429, which we just calculated, times probability of owning a cat, and we get 0.15, which is the value I gave you earlier for the probability of joint pet ownership. So let's see, using the data in table 1, what's the probability of participating in a snow sport given 1 mountain bikes? Okay, so this is important now. You have to be able to do all this stuff on your own using a table. So I need to know what's the probability of participating in a snowboard sport and mountain biking. Okay, if I can figure that out, probability of owning, excuse me, if I have a contingency table, probability of participating in a snow sport and mountain biking. Okay, that's yes to snow sport and yes to mountain bike, and they intersect at 45, right? So 45 out of 1,000 people both snowboarded and skied, or skied and mountain biked. Okay, that's where they meet. That's where they intersect. That's a joint point. That's what we get here, 0.045. 0.45 divided by, I mean, sorry, 45 divided by 1,000, right? So you divide this by 1,000, you move the decimal point 3 places to the left. So right now there's an invisible decimal point to the right of 5 here. Move it 1, 2, 3. So we get 0.045. Okay, that's here. Probability of mountain biking. Well, I think we already did that, right? Yeah, here it is. Probability of mountain biking is 0.140. So I can calculate the probability of participating in a snow sport given 1 mountain bike, 0.321, or there's a 32% chance. General multiplication rule. We used this earlier to calculate, to assess whether we had independence, right? Didn't we? And I said two things were independent if the probability of A and B is equal to the probability of A times the probability of B. Well, if B is independent of A, right, then this A will have no impact on B at all. So we can eliminate that A. So that's how we got that independence test. All right, so and means multiplication or means addition. Okay. What's the probability of participating in a snow sport and mountain biking? Well, we already did that, right? Snow sport and mountain bike, that was 45 divided by 1,000. But we can actually use the so sometimes I'll have you do it directly from a table. Like you can go 45 divided by 1,000, boom, you're done. But I may say, no, you have to use the equation to do it. So if you have to use the equation, we use the one that I showed you earlier where we rearrange that multiplication rule. To get the probability of snow sport and mountain bike, we do the probability of participating in a snow sport times the probability of mountain biking. So the probability of participating in a snow sport, there were 70 out of 1,000 people who did that, right? So it's 0.070. The probability of mountain biking given one participates in a snow sport. Okay, here's the first time I'm showing you how to calculate a conditional probability just by looking at a table. So it's a probability of mountain biking given one participated in a snow sport. So I have to restrict my sample to the yeses here, those who participated in a snow sport, right? There were 70 people who participated in a snow sport. So the question is, what's the probability of mountain biking given one participated in a snow sport? Well, 45 of those 70 mountain bike, right? 45 plus 25 equals 70. So 45 divided by 70 would give me that probability. That's how I got that. So the probability of participating in a snow sport and mountain biking was, by this equation, 0.070 times 0.643 gives us 0.045. Voila, that's our answer. Well, if you look at this, that's exactly what we got earlier when we just divided 45 by 1,000. What's the probability of participating in a snow sport and not mountain biking? There's lots of different ways we can do this. Probability of participating in a snow sport is 0.70. Probability of not mountain biking given one participated in a snow sport. Well, we had 70 people participating in a snow sport. 25 did not mountain bike, so 25 divided by 70 would give us that answer. 25 divided by 70. But it's also, if you were interested, it's also the complement of this mountain biking given one participated in a snow sport. So among those who participated in snow sport, you could have either mountain biked or not mountain biked. So the difference between the two, right, would give us the answer. Oh, not the difference. We subtract this value from one, right? 1 minus 0.643 would give us the complement of mountain biking given one participating in a snow sport, and that's 0.357. So you can do it either way. That's fine. We multiply them together, we get 0.025. So that's the probability of participating in a snow sport and not mountain biking, right? The same as 25 divided by 1,000. Let's just talk about this thing called the total probability rule. That seems to not make sense here why we're doing it, but it will make sense in a moment why we do that. So it's the same as a marginal probability. Like I say, what's the probability of A? So bear with me when we do this here. So let's look at A here, right? What's the probability A? So A includes this part that looks like a Pac-Man or kind of like a partial moon right there. So that's the probability of A intersection with anything outside of these, the not B. So it's this little area right here, plus the probability of A intersecting with B, which is that little football shaped part right here. Now, you'll see why we need this in a second. So what's the probability of participating in a snow sport? Well, think about it. Participating in a snow sport, you can either mountain bike and participate in a snow sport, or you can not mountain bike and participate in a snow sport, but that makes a snow sport. So the probability of mountain biking and participating in a snow sport we calculated earlier was 0.0455. Probability of not mountain biking and participating in a snow sport, that's right here, is 0.025. So we add those together, we get 0.07. That's the total probability of participating in a snow sport, right? 70 divided by 1,000. And that's going to come in handy now. Let's get to the important stuff. Yeah, screening test. So in medicine, we do a lot of screening. We do screening for cancer. We do screening for COVID. You probably took a ton of COVID tests over your lifetime. We're always screening for something. Well, screening tests aren't not foolproof. So two things we want to calculate for screening tests are the sensitivity and specificity. These are properties of the test. Look, if you read the manual in a test, you'd see you could get its sensitivity and specificity. Hopefully they'll write it the way they're supposed to write it. So sensitivity means the probability of, let me see if I can here it is. Sensitivity is probability of testing positive given one is disease positive. That's your sensitivity. It's a probability, conditional probability. Specificity is the probability of testing negative given your disease negative. So what does that mean? If you're disease positive, you should test positive, right? If the test is any good, if you're disease negative, you should test negative. These are true negatives and these are true positives. Those are other ways to look at it. It's hard to remember these terms sometimes, which goes with which. I think of sensitivity as being sensitive to somebody who has the disease. I don't know. That's the best I could come up with in terms of remembering it. One of the things you're going to have to do on an exam is complete a contingency table like this one. So I'll start by giving you a set of values, and then I'll ask you to fill in 1, 2, 3, 4, 5, 6, 7, 8 values. I'll give you the sample size, and I'll give you the sensitivity and specificity. But we should also be able to work backwards and calculate the sensitivity, specificity, and the probability of a false positive result using this table. So let's go ahead and do that. I think I have it. Yes, I have it here. Where did I put that? This is I think it's the one before. Yes, it's the one before. All right, so sensitivity. Well, we have. All right, how do we calculate the sensitivity here? That's the probability of testing positive given one is disease positive. We have 2,000 disease positives and 1,850 of those tested positive. So 1850 divided by 2000 would give us the sensitivity, right? Would give us the sensitivity. And here it is. Let me just move this. Here it is. So we have 1850 divided by 2000, or 0.925. Okay. Specificity. Well, it's the probability of testing negative given one does not have the disease. So 48,000 individuals do not have the disease. Of those, 40,800 tested negative. So the probability of testing negative given one does not have the disease is 40,800 divided by 48,000. And what did we get here? We got 0.85, 40,800 divided by 48,000, 0.85. False positive. Well, let's think by definition, what is a false positive? A false positive is the complement of specificity. Specificity is testing negative given one is disease negative. So its complement would be testing positive given one is disease negative. Find the probability of a false positive. We just subtract specificity from 1, right? Because it has to equal 1 because that's the sample space. So 1 minus 0.85 is 0.15. That's how I got that. All right. Next step. This is an example of something you have to do in class or in exams, I should say, sorry. You have to complete this table. You're only going to get this value. You're going to get the sensitivity and specificity and the prevalence, disease prevalence. That's how much disease there is in the community. Like 4% of the population has the disease. And we're going to use that to complete this table. All right, let's do that. Yep, here we go. 90,000. And we have our sensitivity and our specificity. So I had our prevalence is 0.04. I said 4% of the population has the disease. 4 divided by 100 is 0.04. I said the sensitivity is probability of testing positive given one is disease positive, 0.925. Specificity, probability of testing negative given one is disease negative is 0.85. So I could use these values to fill out this table. To get the first value, the number of disease positives, I take 0.04 and multiply it times 90,000 because 4% of 90,000 have the disease, and that's 3,600. Well, if 3,600 of 90,000 have the disease, that means the remainder do not have the disease. So I go 90,000, which represents 100% of all values, right? Because there's 90,000 individuals, so 90,000 minus 3,600 would give me that 86,400. So 1, 2, 3 cells are done. Next step is to fill in these 2 cells. Well, these are the true positives, right? So we can work back from that sensitivity equation to fill this in. So we know that the probability of testing positive given your disease positive is 0.925. That means 92.5% of these 3,600 are true positives. So 0.925 times 3,600 is 3,330. The remainder of these are what we call false negatives, right? Because they tested negative, but they do have the disease, so they're false negatives. So we do 3,300, subtract that from 3,600, we get 270 individuals. We've got 1, 2, 3, 4, 5 cells complete. Let's go to the specificity. Specificity 0.85, probability of testing negative given one is disease negative. So we know that 85% of these true negatives right here, these negatives are people who don't have the disease will test negative. So it's 0.85 times 86,400. We get 73,440. The difference between these two would be the remaining 12,960, or those are our false positives. So now we're almost done. Last step we have to do is add these two together to get the total. Add these two together to get this total. Same here and here. We add these two. Well, we already have those, so we don't have to worry about that. And we just got to make sure that everything adds up. Like this plus this has to equal 90,000. This plus this has to equal to 90,000. And we're done. That's how you complete that table. Sometimes I may ask you to verify the sensitivity and specificity as well. I might ask you to work your way backwards, kind of like we did with the first problem. All right, the last thing I want to talk about is something known as positive predictive value, or the PPV. So to calculate PPV, we can use something known as Bayes' theorem. Now, by definition, PPV, positive predictive value, is the probability of having a disease given one tests positive for the disease. And if we have a table, we can figure that out. Like from this table, I could figure that out easily. So I'd say probability of having the disease given one test positive. Like we know here, 9,050 people tested positive, and 1,850 have the disease. So if I divide 1,850 by 9,050, I have my answer for my PPV, positive predictive value. However, we don't always have access to the table. Instead, I can give you certain values. And if I give you those values, like the sensitivity, prevalence, and specificity, you can calculate PPV using Bayes' theorem. Okay? Bayes' theorem, that's this is a conditional probability. It's a probability of A given B. And we've seen this equation before. It's probability of A and B divided by the probability of B. But now I break it down into that equation that I showed you earlier. Like what's the probability of A and B? It's the probability of B given A times the probability of A. Here's the total probability of B. That's why we did that earlier. It's the probability of B given A times the probability of A. So that's one part of this probability. Or it could be the probability of B given not A times the probability of not A. See, that's why I told you we had to do that. All right. In epidemiology, we study diseases. So we calculate PPV because that's very informative. We can tell whether or not we need to screen for a test. If the screening has a high PPV, that means it's something worth doing. So we can convert this equation into the following equation. So the PPV is the probability of testing positive given one is disease positive times the probability of being disease positive. And then we have the total probability of testing positive in the denominator. That's a probability. You could either test positive and be disease positive, or you could be testing positive and be disease negative, right? That's why we break this down in the denominator. Each of these is related to one of the definitions I gave you. So this first element is sensitivity. The second element, this is just the probability of the disease existing in the community. So that's prevalence, right? Probability of being disease positive is prevalence. Like if I said there's 4% chance, there's 4% of the community has the disease. If I pick any one person from the community, that individual has a 4% chance of having the disease. The denominator is the total probability of testing positive. So this again is sensitivity and this is prevalence. So this first element here is always equal to the numerator. And the second element, well, we have the probability of testing positive given one is disease negative. Testing positive given one is disease negative, that's called a false positive. And we learned earlier that's 1 minus the specificity. And then we have the probability of being disease negative. Well, that's 1 minus the prevalence. So those are all easy to calculate. You keep track of everything. All right, so here's the last example I'll look at. I think, yeah. Well, actually, let's go straight. Which one should I do? I'll do this one, and then you can work on the other ones on your own. Like this last one, you can work on your own. I'll give you the answer so you can have it. Okay. All right. Using the data in table 4, table for what's the prevalence. Well, the prevalence to calculate that's just 500 over 10,000. That's how much disease that there's in the community, right? Just that's how much disease there's in the community. So let's go to, I think I should have that. I think it's right here. Maybe. Let's see. Hold on. Actually, yeah, that's how much disease is in the community. It's 500 over 10,000. All right. And then what's the sensitivity? Well, the sensitivity I already gave it to you. It's 0.99. And what's the specificity? It's 0.95, but you could calculate the sensitivity 495 divided by 500. And the specificity is 9025 divided by 9,500. What's the probability of a false positive result? Well, if our specificity is 0.95, right? As I mentioned, false positive, probability of a false positive is 1 minus specificity. 1 minus 0.95 is 0.05. That's everything we need. And if we want to now we want to calculate the PPV. It says using Bayes' theorem, calculate the PPV. So we need sensitivity, specificity, and prevalence. And we have all those data. So let's put this together, all right, and complete this assignment. Or this example, I should say. All right, so the probability of testing positive given one is disease positive is 0.99. We got the specificity is 0.95. The prevalence is 0.05. So we're going to plug this into our equation. So here's our equation, right, for Bayes' theorem. You know, I wrote it down two different ways here, right? But this is basically what we're looking at. Probability of testing positive given one is disease positive. That's your sensitivity. That's 0.99. Your prevalence is 0.05. So it's 0.99 times 0.05 in the numerator. Remember, the first element of the denominator replicates the numerator. So again, it's 0.99 times 0.05. Sorry for this messy writing here. The probability of testing positive given one is disease negative, also known as the false positive probability, is 0.05 because it's 1 minus the specificity. Specificity is 0.95. 1 minus 0.95 is 0.05. And finally, the prevalence, we know the prevalence is 0.05. 1 minus the prevalence is 0.95. Multiply this. Remember, everything that's within these brackets is multiplied together before you add it to everything that's in this bracket. You do that multiplication first as well. So we get 0.0495 divided by 0.0495 plus 0.04. I believe that's a 75. And we get our specificity, excuse me, our PPV, a positive predictive value, to be 0.51. You can check your work by going back to your table, right? Going back to your table, wherever that table was here. So by definition, PPV is the probability of, actually I had the prevalence here, the probability of being disease positive given you test positive. So 970 tested positive. So 495 divided by 970. 495 divided by 970 equals 0.51. That's the same thing that we calculated. So they work out. I'll leave this last one for you to do on your own, but I'll put the notes in there as well. Plus, you have stuff in the book that you can work on. Thank you very much for a wonderful day and enjoy the rest of this week. Bye.